All right, so the topic we're talking about now is chemical kinetics. And this specific module is about reaction rates. So, first of all, kinetics, chemical kinetics, deals with how fast a chemical reaction occurs. Now, up to this point, we've talked a little bit anyway about spontaneity. Will a reaction happen, spontaneously by itself? Um, for example, the combustion of hydrogen, or the reaction of hydrogen with hydrogen gas and oxygen gas, that happens spontaneously, but if we talk about the rate, it happens really, really slowly. We could take a balloon, I've done this, fill it with hydrogen, a mixture of hydrogen and oxygen, let it sit there, nothing, right? But if we give it a little bit of heat, then it'll go. So the question is, how fast does it happen? Now, we're going to start out talking about an example, a sample reaction, the decomposition of nitrogen dioxide gas at 300 Celsius into nitrogen monoxide gas and oxygen gas. 300 Celsius is just, it happens to be the temperature that we're talking about here. Now, for this reaction to happen, okay, what has to happen is 2 molecules of nitrogen dioxide. In this little picture here, the red spheres represent oxygen and the gray represents nitrogen. They have to come together, and when they do, and we'll talk about this a little bit later, but they have to come together with enough energy. If they don't have enough energy, enough kinetic energy when they hit each other, they're just going to bounce off. Nothing's going to happen. And they also have to hit each other with the right orientation. If I flip this one backwards, and the oxygens here hit the nitrogen there, then it might not happen. We'll talk about that a little bit later. But we make 2 molecules of nitrogen monoxide and 1 molecule of oxygen. Now, this represents the overall reaction. It ends up that a lot of chemical reactions happen in a series of steps. It's a much more complicated mechanism than it appears here. We'll get to that later too. But let's look at what happens here. So this graph here shows how the concentration of nitrogen dioxide, that's this green line here, changes over time. This is concentration in moles per liter versus time in seconds. And it curves down like this. And so, and the blue line here is the appearance of nitrogen monoxide, and this one is the appearance of oxygen. So at time 0, we don't have any nitrogen monoxide or any oxygen, and we have, in this specific example, 0.01 moles per liter of nitrogen dioxide. As nitrogen dioxide decomposes, we start to see some of the products appear. And this is a table of the data that was used to make these graphs. Now, when we talk about the rate of reaction, what we're talking about is how fast either a reactant disappears or how fast a product appears. In general, the rate can be written down as this, where A, the capital A, represents either a reactant or a product. And remember, the square brackets mean molarity or concentration. So this is the concentration of A, whatever it is, reactant or product, at the second time minus the concentration of A at the first time, divided by the difference in time, T2 minus T1, or we write it like this, delta concentration of A over delta T, remembering that the delta means the change of final minus initial. For example, for the first 50 seconds, the average rate is going to be the concentration of nitrogen dioxide at 50 seconds minus the concentration at 0 seconds over the difference in time, which is 50 seconds minus 0 seconds. So if we put the numbers from the chart in here, plug them in, we actually get a negative number. And that's because the nitrogen dioxide is disappearing, so its change in concentration is negative. However, we always define rates as positive numbers. So if we're dealing with a reactant, we always put a negative sign in front here, which makes it a positive number. So put these numbers in, and we end up with about 4.2 times 10 to the minus fifth, and the units are moles per liter per second. That's an average rate. Okay, and we'll come back to that. Now let's look at the second 50 seconds, right? So from 50 seconds to 100 seconds, same nitrogen dioxide. Delta concentration of NO2 over delta T, negative because it's a reactant. Plug these numbers in, and we get 2.8 times 10 to the minus fifth moles per liter per second. It's different. It's a different number. And if you look back at that curve, you see it's not a straight line. So the rate is the slope of the curve is changing, which means that the rate is changing. Now, those are average rates. So over the first 50 seconds, that was on average the change in concentration of nitrogen dioxide over time, and the same thing for the second. If we want the rate at a specific instance, called the instantaneous rate, what we need to look at is the slope of the tangent line at that point. For instance, here, at 100 seconds, if we were to draw the tangent line to the curve for nitrogen dioxide at that point and find its slope, rise over run, all that good stuff, plug it in, we would get a different number, 2.4 or so times 10 to the minus fifth moles per liter per second. Notice, again, because this is a reactant, we put the negative sign in front. So if we want the instantaneous rate, we need the slope of the tangent line. If we want an average rate, then we can just put in the change in the concentration over the change in the time over that range. Now, if instead of looking at the disappearance of a reactant, we can look at the appearance of a product. And so, okay, for this specific reaction, if we look at the appearance of nitrogen monoxide and oxygen going from the same table, the rate now is going to be, we don't put the negative, it's positive because it's the appearance of a product. The negative's only there if it's a reactant and it's disappearing. So, final 0.0021 moles per liter minus 0 over the change in time gives us 4.2 times 10 to the minus fifth moles per liter per second, which is the same as the disappearance of the nitrogen dioxide, except same rate. But look at oxygen, right? Now if we put those numbers that we have here, we get a number 2.1 times 10 to the minus fifth moles per liter per second. That's half the rate of the appearance of nitrogen monoxide and half the rate of the disappearance of nitrogen dioxide. And we can see why that is, if we go back and we look at, actually let's do it this way. If we look at the original equation, it was just this. I'm just looking at the stoichiometry here. For every 2 molecules of nitrogen that decompose, we get 2 molecules of nitrogen monoxide that appear. So the rate of disappearance of nitrogen dioxide should be the same as the rate of appearance of nitrogen monoxide. But the coefficient for oxygen is 1, which means that for every 2 molecules of nitrogen dioxide that disappear, we only make 1 molecule of oxygen. So its rate of appearance, oxygen's rate of appearance, will be 1/2 the rate of disappearance of nitrogen dioxide, and thus the rate of appearance of oxygen will be half the rate of disappearance of nitrogen dioxide. And at this point, the important thing is that we get out of this is that we have to be careful when we're talking about rates about specifically what are we talking about? Disappearance of a reactant, appearance of a product, which one?